Okay. So, basically a couple of results and then we will conclude today's session. So, the polyphase implementation of a multi-carrier system. Multi-carrier system goes back to a few slides. Okay, this is my multi-carrier system. Remember, with redundancy we have introduced n, which is some value larger than m. So, I want to draw the redraw the equivalent diagram for us in the context that we are looking at. Okay, so first we start off with just representing the synthesis filters. I will just write down the results because we already have obtained these results before. F1 of z, Fm minus 1 of z. We will split this into n polyphase components. So, it will be a row vector 1 z inverse all the way to z power n minus 1, followed by a matrix which is an n cross m matrix. I will not write down everything. This is G00 z power n, G10 Gm minus 1 comma 0, these are all z power n's, all the way to G0 comma m minus 1 z power n all the way here. Okay, this is the synthesis filters. The analysis filters, remember we needed it with the powers of z. So, the definition that we have used before using the shifted versions, H0 to H m minus 1 of z. Did I use some other name? N minus 1, absolutely correct, thank you. Yeah, it is n minus 1. G n minus 1 comma 0, then I better write the last one also so that there is no confusion. This one should be G n minus 1 m minus 1 comma m minus 1 z raised to the power n. Okay, these are all z power n terms. Okay, now h of z, this the analysis filter bank with the powers of z will be S00 z power n, S01 z power n, all the way to S0 comma n minus 1 z power n, n polyphase components. The last one is Sm minus 1 comma 0 z power n dot dot dot. The last one is Sm minus 1 comma n minus 1 z power n, n minus 1 polyphase component of this. Okay, so basically we have obtained this one. Oh, I forgot the 1 z z squared z power n minus 1. Okay, so this we have obtained using the type 2 polyphase decomposition, and the other one using the type 1 polyphase decomposition. You can fill in those data. Okay, so the final representation in terms of this transceiver with redundancy in our context can be represented as follows: a trapezoid which represents G of z. It has m minus 1 inputs, S0 to Sm minus 1, S0 of n, Sm minus 1 of n, that is the last input. I produce n outputs, label them as x0 of n all the way to x n minus 1 of n. Each of these is upsampled by a factor of n, upsampled by a factor of n. Maybe I should have just written it as parallel to serial conversion. Okay, all of these are added with a delay chain. Okay, maybe it is worth it because it helps us to visualize the full picture with the delay chain. all of these added up, these are all delay chains. This comes out to be the signal x of n, which is passed through the channel C of z. There will be a noise term, but really in our analysis noise is not going to play a picture. So, I am omitting that, but you can perfectly okay to introduce that. At the receiver you have these parallel channels downsampled by n. Notice it is an advance operator, z downsampled by n such branches downsampled by n. We will introduce a label for these, it will help us in our analysis. We will call this as R0 of n, R1 of n, Rn minus 1 of n. There are n signals which are then combined by another trapezoid, basically another matrix which is not a square matrix, it is a rectangular matrix, takes n inputs and produces m outputs. So, the outputs this is S0 hat, S0 hat of n, S m minus 1 hat of n, and what is sitting inside is S of z matrix. This G of z is also a matrix. Okay. So, this is our representation. Okay. Now, as an exercise I would like you to do the following. Do a polyphase decomposition of C of z. Okay. So, basically do a polyphase decomposition of C of z. What will happen? In this structure you will get the following. You will get C naught of z power n. Do a type 1 polyphase decomposition, that is simple. Z inverse C1 z power n, z power n, I wrote m, it is z power n, and so on until you get C n minus 1 z power n, with all of these are through the delay chain. Basically I am just rewriting C of z by a summation and then add up all of these. Okay. Now, leave off this G of z, draw a line here, and likewise we will for the moment we will not worry about S of z, draw another line here. Look at what is in between. You have a parallel to serial converter through a delay chain using the delay chain, then a channel which has been implemented in the polyphase form and a serial to parallel converter at the other end. Okay. Now, is this an LTI system? Very important question, because anything to the left of the green line is LTI, anything to the right of the green is LTI. Now, can this be represented as an LTI system? Very, very important question. The answer turns out to be yes. Okay. Why? Because the transfer function between x naught, trace the line between x naught and s naught. X naught can and r naught. X naught goes through an upsampler. Okay. And it can go through any one of these branches, you can assume that it is going through all of the branches, and at the other end it goes through a downsampler. Which of these will survive? Only C naught will survive, because all the others will get killed, because it is an upsampling followed by a delay followed by the downsampling. And why is that? Because this downsampler can move to the left of the using the Noble identities, it can move to the left, and therefore the input output relationship between the R naught of z, R1 of z all the way to Rm minus 1 of z okay, is actually a transfer matrix where I will just write down a few entries and request you to finish the rest. The inputs are x naught of z, x1 of z all the way to x, is it m minus 1 or n minus 1? It is n minus 1, I am sorry. So, this should be n minus 1, n minus 1, and here we will have x of n minus 1 of z. Okay. Between x naught and r naught, the transfer function turns out to be c naught of z. Why is it not c naught of z power n? Because the downsampler moved and you had the noble identities. Okay. Between x1 and r1, x1 and r1, x1 comes in with the upsampler followed by one delay unit, passes through c of z. So passes through you can pass through any of these branches, and at the other end R1 comes out with a one advance operator. So, the z inverse and the z will cancel each other, leaving the transfer function to be only c naught, all the others would have gotten killed. So, R1 to x1 to R1 is also c naught of z. Okay. Now, just one more entry and then we will be done. Between x naught and R1, x naught goes in without any delay change, only the upsampler. R1 comes out with an advance operation. Which of these branches will survive? C1, only C1 survives. So, basically this becomes C1. Okay. Now, if you go in and complete the rest of this matrix, you will find that all the main diagonal elements are C naught of z. All the one lower diagonal, all of them are C1s, okay, and all the way up down here C1 of z. Then comes C2, C2 of z. Now, any matrix that has got this is called a Toeplitz matrix. Okay. Now, very interesting. What is the transfer function between R naught and x1 will basically be the second element here, right. So, if you go ahead and fill out all of these entries, this last one will be Cn minus 1 of z. Okay. Now, the important question is, what is the transfer function between x1 and R naught? x1 is basically enters through one delay element, can pass through any of these branches of C of z, and then R1 is the one with one advance operator, right? No, R naught. So, there is no it has to just go through the downsampler. Okay. So, there is a z inverse. If it goes through any of these branches, it will get killed because of the downsampling. The only branch that can go through is the last one, because it will have z power minus n when I downsample. When I downsample, I will get the transfer function to be z inverse times Cn minus 1 of z. Okay. And then you will get a Toeplitz matrix of z inverses. The next one is going to be z inverse of Cn minus 2 of z, again a Toeplitz matrix. Okay. So, basically what you see as a transfer function between the x vector and the r vector is actually an LTI system. It has got a very interesting and important structure, because the transfer function is a Toeplitz matrix. In addition to being Toeplitz, it is also got a circulant property, because what comes if you take the first column C naught, C1, C2 all the way to Cn minus 1, you will find that the next column is just downshifted by 1 with a circular wraparound, and when Cn minus 1 of z comes to the top, it comes out with a z inverse. Okay. Now, this type of matrices have got, so basically this matrix has got a property called the Toeplitz property, all the diagonals are the same, and it has got the circulant property, but it's circulant means the last term just appears at the top, but it appears with a Z inverse. So, it is called pseudo circulant matrix. Okay. So, replace this multirate part with G of Z, a pseudo circulant matrix followed by S of Z. Okay, that's how far we have been able to come. Now, it turns out that we can now start to actually show what are the relationship between G, this transfer function C, and S of Z in order for us to start being able to design very powerful types of systems, and we can also show where the design elements of multi-carrier systems will come into play. Okay. So, we will stop here, but we have covered introduced some new notation, also introduced some concepts which if you can read the corresponding chapter in Untitled, it will be very helpful. More or less I have used exactly the same notation, so that there should not be any confusion, but we are now at a point where we can move into the design of multi-carrier systems, where we can eliminate inter-carrier interference, intra-subcarrier interference, and actually be able to design very efficient systems. But the key question is, I have introduced redundancy, how do I exploit it? Okay. So, this whole now what comes into play is how do I exploit the redundancy in the system that we have designed. Okay. We will stop here, we will pick it up from here the next class. Thank you very much.